Okay, we have the integral from 1 to infinity, x to the s minus 1 minus x to the z minus 1 over 1 minus x to the a dx. And this is kind of like part 2 of 2 videos. The last one we did is really the same integral, but going from 0 to 1. The difference here being, if you wanted to use geometric series on it with this kind of denominator, well, in this case, you don't really have the convergence because the convergence for geometric series needs to be absolute value of the input less than or equal to 1. So it doesn't really work here, and we will have the assumption we want a greater than 0 because that's going to come up here later. Now you will see later on that you could still use geometric series after a substitution, but I'm not going that way. I'm just going to use this other formula that we derived earlier, and if I can get this into this form, then we can kind of use this and finish it. So to get started, I want to do a u substitution. In the last video, we did u equal to x to the a in order to clean that up. Now, just a little bit different, I want to do ux to the minus a, which is the same, of course, as 1 over x to the a. If I solve this for x, we have x equals u to the minus 1 over a. Then let's get our dx value, take a derivative. So dx with power rule is going to be minus 1 over a u minus 1 over a minus 1 du. I'll go ahead and substitute now. First, plugging in infinity, this is where the a greater than 0 really matters, because with a greater than 0, we can say this is going to 0. If you had a negative value for a, you'd be going to infinity, totally different problem. So here, plugging in 1 to the minus a, that's just 1. Next, for x to the s minus 1, we'll plug this in here. What I can do is use the minus sign to reverse the sign on it, right, as 1 minus s over a. Same exact thing on the z, just a different variable, so this is going to be 1 minus z over a. Then here, this is all going to become 1 minus u, and then our dx is all this stuff. So let's bring the constant part out front, minus 1 over a, and then we have, I'm actually going to split this up, I think, and I think I made a mistake already. 1 second. So I'm going to split this up as u minus 1 over a times u to the minus 1, which I can write in the denominator as just a u. And the mistake I made here, if you do the reciprocal here, x to the a is going to be 1 over u. So this thing should just be a 1 over u right here. And the reason I split this up is because I want to take this u and distribute it into the numerator, and I want to just take this part and distribute it into the numerator. So when I do that, let's see what we have. We still have minus, and actually let's use the minus sign to flip the bounds here. So I'll write it as 1 over a, minus sign to flip this to 0 to 1. Then we'll do the numerator. When you distribute this in, if you break this up, like for u 1 minus s over a, I could break this up as u 1 over a minus s over a. Then we're multiplying u minus 1 over a. What's going to happen is when you multiply together, add exponents, this cancels with this, and you just get u minus s over a. So we'll do this. The z value is going to work exactly the same way. Then distributing in this u, we end up with just u minus 1 du. But I really want to reverse this denominator so I can use my formula. So if I multiply in a minus, I can change it and bring a minus out front. And let me just switch the order on this. Now, one last thing I want to do on this in order to use this formula, I want to mess with these exponents. I can add 1 on each exponent, but so I'm not changing it. Let's subtract off 1. This way we're just adding a 0 in the exponent, doesn't matter. And then I'll kind of group it to make it clear, like this. And so what just happened is this is going to be the input into this formula here. So what's going to happen, we're going to have minus 1 over a in front. Then going to the formula where, like, okay, so this s is getting input here to make it clear, or more complicated, whatever you choose. And then this z is going right here. So what we're going to have first is this input. So we're going to have digamma of 1 minus z over a minus the next one, digamma 1 minus s over a. Then just cleaning it up, let's take the minus sign and reverse everything and bring it all over a. So what we're going to have for a solution of this, digamma 1 minus s over a minus digamma 1 minus z over a, all over a, and that's it. So it's a pretty nice formula. When I first did this, I asked what would happen What if this thing was actually not starting at 1? What if it was going from 0 to infinity? Well, we definitely have a nice way to deal with that. Just let me get a little space and I'll show it. Okay, so maybe it's a little obvious if you saw the previous video, but in that one we derived this right here for the integral going from 0 to 1. As we broke it up, integral from 0 to infinity with kind of a large 0. We can break it going from 0 to 1 and 1 to infinity. This is the formula we just found in this video. But then we have the common denominator, we pull it all together, kind of rearranged it a little bit, because what I wanted to do is get this in the form of the reflection formula for our Digamma function. Because then using the reflection formula on this piece and this piece, we can put it into this form of cotangent, and we have kind of a nice compact formula, especially if our S, Z, and A values are kind of nice. Depending on those values, it could get messy, but in a lot of cases, this should work out to something nice. Okay, that's it for today. Thanks everyone for watching. Have a good day.